this computer. Okay, let me jump to the textbook, because that's a great question, and that's something that I got to figure out, as well as inform you guys when I send the email out this week, because yeah, the test will do the main part of chapter 30, but not quite the whole thing. And the main part is sections 1 and 2 and 3 and 4, and that's where we'll stop. And I think that's what I said in the lecture. That's the part I need to check with, because the next part, which is sections 5, 6, and 7, although maybe I think I say something about 7, but definitely I think what you were asking about, did I hear you right, Dan? You said 6, but I would even put 5 in there. 5 is really best addressed as the beginning of chapter 31, and 6 we kind of touch on. There's 2 homework problems, gladly answer them, but it's one of these things where we're kind of also transitioning into what would be your next level of course. And so it's good. I'm glad the author has it there. I don't think I really touch on anything during the lecture part of it. It's just kind of, that's the transition point between what you get in a first class of magnetism and a second class of magnetism. So it's kind of that boundary line there.
Okay.
So that was a long way of saying that the test would only be sections 1 through 4. 7, there's no real testable material on it, but it's nice and good to talk about the magnetic field from the Earth. So I would call that part of 30, but not really testable material. So I don't know if that helped. So I think that's probably what I'll write in Sundays when I give the weekly assignment, because this week's assignment will be about preparing for the test. And if you're behind in any way, then keep working towards it. The test is what, Tuesday the 3rd, so we're still a little ways out. Let's see, Tuesday the 3rd would be 14 minus 3, so 11 days away. And all next week is going to be kind of a catch-up week if you're behind, or go ahead and work into the next chapter if you feel like you're ready for the test. Only, I think I said that same thing on the first test here.
Okay, cool. Thank you.
Yeah. So I'll need to keep saying that today and mention that. So as you'll see, I don't know if anybody's going to ask anything, but I believe I was just scanning through the homework problems, and I noticed, I believe 2 of them talked about the magnetization of materials, or maybe even 3 of them. And those would be good to do, but like I said, really kind of that transition into the next level of class. So it would be to your advantage to see it a little bit, but maybe not test you on it. So that's kind of my thinking. All right, well, good. I'm glad I called up the book here. Let me do a couple other things before we really get completely started. Let me call up, oops, the let me call up the other textbook, being the 122 class. We'll slow it doing that. Okay, I'll take both of those. Let me also come down here to both 102 class, in case anybody kind of pops in from 102 and open up the homework for 102. But I know a lot of you are doing some real hard stuff now in 122 here. 102, and now let's go to 122. Let me call up the homework from it. Where is the homework. Oh, and that just reminds me that I'll call it that homework, but I'm missing a page from chapter 30 that hopefully you guys all got. And let me find that. Here it is. Call that up. Okay. Nice. And so that'll be the homework and the textbook. Oh, and you guys should also get going while I'm here. The solution page, that'll give me a quick link to the solution page for 122 and the solution page for 102, should we need to look at that. All right, so I think I'm finally got my stuff ready to go. I'll switch back here to Zoom, and I'm not sure who was here first, but I'll say the same thing as I always do. Let me open up the chat, and oh good, some of you are already there. And I'll just go in that order that's the only way I know how to make it kind of fair here. So could you do chapter 30, number 36? Good, and then there's a 27, okay, good. Oh, and then there's a one from a 121 too, 121 class, two, or also, I should say, not two, so it's confusing. Yeah, perfect, all right. So with that in mind, let's see, Andrew, I guess you asked that one. All right, let me go to the questions here. All right, so, oh, and I forgot already what it was. So number 36. Oh, and let me take this as an opportunity to write down. So something some kind of record to send to everybody. So chapter 30, the first session, and we'll do number 36 here first. And it is about 10:09. I think I started the recording about 10:02. Should have looked. 10:02, 10:03.
I started a stopwatch. It's at 7 minutes, 20 seconds right now.
Thank you. All right. That does tell me then I started at 10:02. So good. I'll write that 10:02. And so I can write this then at 10:09-ish. And now we can jump over to the homework. I'm going to guess that that's on that first page, the missing page, number 36. Yes, it is. Okay. And now, come on, when I started, it makes it so tiny. All right. Oh, number 36. Oh, yeah, I was reading this one last night. This is a killer. Okay. I can see why you're asking it. This may take a while here. All right. Let me set up my camera. We'll slow it doing that. I was trying to finish a survey this morning, and I answered some emails, and then I go, oh no, I haven't really set up. So time got a little bit away from me. However, I'm here now, and let me just adjust my settings to make sure it doesn't go to sleep. Okay, there we go. Let me also plug in the power so that we don't run out of power partway through. That looks good. All right, the camera then is set up. So now I'll have to go to my share the screen and find the camera. Good, okay, share. All right, now I got to Bluetooth it together, and I think we're good. Let's take a second. There we go. Working, back to the screen, nice, and we're in real time. Okay, so let's work on this. This is a finite size solenoid and a heck of a problem. And as you'll see, this is exactly the idea that I was trying to warn you about in my email on Sunday, that you need to think of these problems a lot like we did at the beginning of the semester, where we did Coulomb's law, where to find the electric field, we knew what it was from a point, and we added up a bunch of points. So in this one, we're trying to get a finite length solenoid. We could think of the finite length solenoid as being made up of a bunch of rings. Let me kind of show you with pictures here. All right, so chapter 30, number 36. And this problem says, consider a solenoid of length L. All right, so I'm going to make a little cylinder, maybe start it here and have it go back a distance to here. And so the length of the solenoid is a distance L. That's kind of my three-dimensional drawing, but maybe to help you visualize a little bit better, let me grab a Post-it note here and maybe get a white background. But if I just kind of roll this up, ta-da, I have my solenoid. So that's going to be my solenoid, and I'll keep it handy in case I need to come back to that. And this problem says, so consider a solenoid of length L and radius capital R. All right. So maybe over here, I'll put capital R for the radius. Containing N closely spaced turns. All right. So the current would come up over the top, around behind, up over the top, around behind, up over the top. And so there's a capital N of them. And they don't really say which way the current is going, which maybe they do later on, but they don't give me a picture. All we're going to be able to do is define the magnitude and then, leave it to the direction, either left or right, depending on what way the current is going. And it says carrying a steady current of I. Okay, so here is this current of I. A. It says, in terms of these parameters, find the magnetic field at a point along the axis as a function of the distance A from the end of the solenoid. Okay, so somewhere in this solenoid, so here's the end of the solenoid. I'll put this point, there's the point A. And so what is the magnetic field at this point A? So this distance here is A. And they don't really say whether A is in the solenoid or outside the solenoid, although as you will soon see, it's mathematically would be the same thing. So we're actually going to solve for, maybe not. Let me read that carefully then. In terms of the parameters, find the magnetic field at a point along the axis as a function of distance A from the end of the solenoid. Show that as L becomes very long, B approaches this value at each end of the solenoid. I guess he's not as clear as I thought, but my intention of reading this was really the magnetic field somewhere within the solenoid. I'm going to go with that, and we'll look up the answers here and see what the answers have to say. But the reason I kind of feel like the author is saying that really is based on my experience. When you work with solenoids, the magnetic field is very strong on the inside, and so it's usually what you're interested is the field on the inside. If this was an infinitely long solenoid and an Ampere's law question, which is a much easier one to calculate, again, you'll see that it's the field on the inside that we care about. So I'm going to go with them saying that this A is someplace on the inside, and then just kind of keep in the back of my mind, are they talking about A outside the solenoid? And I don't think so. Yeah, I really don't think so. So that's kind of my picture. But here's the logic behind it. Let's see if I could maybe change colors here. Here's my thinking. I'm going to take this solenoid and maybe think of it as slices, where this first slice right here, and so maybe like a stack of quarters again, laying on its side. This, maybe quarters is a bad analogy, but it's because the current is just on the rim. So this would be something like a ring here. I'll use my wedding ring here. So, so here's the ring, and that ring is stacked, and there'd be another one and another one and another one and another one and another one here. And so, if I draw a second one and a third one, all of these, each of these get a little closer to A. Eventually, one of them is actually in the same plane as the point A, and then the other ones are further away. So again, kind of like taking a metal pipe, so it's hollow on the inside, and cutting it. You would have a ring and 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 a ring. And so the logic I'm trying to get at here is that if you wanted to find then the total magnetic field, you would begin by saying it's the sum of the magnetic fields from a bunch of rings. And so that's why this problem, when you read it, I said, oh, this is going to be a hard one. This is just like we were doing in Coulomb's law, because we learned, the electric field from a point, and then we added a bunch of together to get the total field. And we did all kinds of shapes. We did rods, we did hoops, we did discs. Anyways, we're basically doing the same thing. So that's where I wanted to begin with this problem, was just to kind of let you know kind of the thinking behind it, is that I'm going to think of this solenoid as a stack of a bunch of rings. Now, here's the best thing about that, is we have already derived the equation for the magnetic field from a ring. Let me not rederive it. I suppose I could sidetrack if anybody's interested in that, but I will start with saying, let me just put the equation for the results of a ring first. This is the ring. Now, I suppose I should be careful here, because when we derive this in the lecture and in the manual to figure out what the field was for this ring, A was being the radius of the ring. And so we can get ourselves into trouble if we don't remember that, because A in our problem is not the same as this A. This is the radius of the ring. They're saying the radius of the ring is capital R. So maybe I should cross this out and put capital R squared. And the same thing here, cross this out and put capital R squared. Okay. Now the current is the current in the ring, so that would be the same. And X, if you remember from this, is the distance that we are along the axis of symmetry of the ring. So coming back to this first ring, right, right here, the one on the edge, the X would actually be A. That's the distance of where I'm going to get the magnetic field from that first ring. But then as I move to the second ring, well, now X is going to be a little smaller and then a little smaller. And eventually I'll get to the ring that is in the same plane as A. So X would be 0 then. And then, of course, I would start to get to rings that are beyond this point A. And so X would start to increase again. So this is going to be a variable. This is the part that I'm going to be adding together. I'm going to be integrating on. So I, again, want to keep that in mind here. Now, here's where your knowledge of calculus kicks in. In fact, let me switch my back over to the screen so I can keep an eye on what's going on here. Okay, good. And let me go to the side in case there's a question that pops up here on the chat. But this then is probably best done by taking the next step and saying, okay, now to convert this into calculus, I would take the limit as something goes to 0. And so what becomes really small in this equation, as I kind of imagine taking this cylinder, it's like my Post-it note came undone. But as I slice this into thin pieces, thinner and thinner and thinner and thinner and thinner, what is it that goes to 0 here? Is it the radius? Well, no, as I cut them thinner and thinner and thinner and eventually have an infinite number of them, it's not the radius. In fact, the radius is a constant no matter how thick I cut these slices. So if this is, like a carrot and I'm cutting this carrot, doesn't matter how thin I cut the carrot pieces, they all have the same radius. All right, so it's not the radius that goes to 0. And maybe the biggest one to point out is it's not the x either. I think because of your calculus always having the limit as x go to 0, where x was some variable, it's easy in your calculus to forget that what you meant in your calculus class was not the x that is the x dimension, but x as a variable. Some variable in the equation goes to 0. It's an abstract variable. It is not x as in the x-axis. And that's x in here is the x-axis. And then so as I chop it, you can imagine if I were to hold this here, and I'm trying to find the magnetic field at point A, and I cut this first one thinner and thinner and thinner, the thinner I cut it, x gets better and closer to A. It doesn't go to 0, it goes to A. That's what it goes to. And then, of course, it changes as I go to different spots. In fact, the only place x is equal to 0 is for the cut that is right here at the point A. So it's not x that goes to 0. And, of course, I'm taking a long time to get here. Maybe I shouldn't because this is going to take a while. Well, this is the part that takes a while, is I want you to realize that as I cut it thin here, it's the slice of the currents that is getting thinner. See, as this current comes around and they're really close, you could say, I have a current that, would be occupying some wire. And as I cut it thinner and thinner and thinner, it's the currents that goes to 0. And so as I apply the second fundamental theorem of calculus, which is to change a Riemann sum into an integration, this then can be written as di. And that's a big step. It was a really big step back when we first saw this, when we did Coulomb's law. And it's a big step now. That's way back in chapter 23, where we were adding up chunks of charges. Now we're adding up slices of rings in order to get this solenoid. And so recognizing how to switch the equation of a bunch of rings into an integral is the skill that it's not the first time you saw it, it won't be the last time you see it, but it's still a tough skill to digest. And I'm assuming that you're a little better at it now that you've gone through chapter 23, and that's that big step. Okay, so I'll call that big step number 1. We still got a couple of other big steps, because as you recognize right away, which is why it may have been tempting back here on this part of the problem to then put the dx as going to 0, or the x going to 0, so you'd have this magical dx somewhere. And as tempting as that was, I know why it was tempting. It was tempting because to do this integral, you're going to say, well, I'm going to add up over the x-axis, and that's true. So somehow we have to convert then this di and figure out how it's related to dx. That's kind of this magical step. And if I can use math terms here, this would be the Jacobian of transformation. How could I change it from one variable to another variable? And so from the di to the dx. And so there must be something that looks like this. The di would equal to something which is related to the dx. And that something is what I've got to find. That's the Jacobian of transformation as I transform from one variable into another variable. Okay, so what is that variable? Well, I guess I would kind of look at it this way. Maybe I'll come back to my cylinder up here. And kind of like we did for the charged rod, we looked at the density of the charges. Let's look at the density of the current. That is, if you take the current and you wrap it around n times, you just kind of looked across it, you would say there is a total current going up of Ni. And it would be spread out over a length L. So this would be all of the current over all of the length. That's the density. You would call that perhaps the current density. Current along this is the whole current over the whole length. That must equal then to a small little piece. So if you cut a small piece, how much current is in that small piece? That's what we're talking about, di, over that small length that you made a cut. So a little cut has a width of dx. And so I think I used the analogy of a chocolate bar back in Coulomb's law, and I'm going to say it again. You can take the whole chocolate bar and divide by the whole length of the chocolate bar. Or you could take one little square of the chocolate bar and divide by the area of that one little chocolate, piece of chocolate. And so that ratio should be the same. And so therefore, we can do a little bit of math by moving the dx to the other side, and we have exactly what we're looking for. There is the Jacobian. There's how I change a di into a dx. So let me put page 1 here. All right. So now it becomes more math than physics, because this integral would be the mu naught, and I'm going to write the r squared first, and now I can put this di. So this is ni over L dx. So there's the di that would fit into here, okay? And so that's the numerator. Now, in the denominator, I still have the 2 and the r squared and the x squared and the 3/2 power. Okay, so now I have things labeled as I hope that I want, which is in terms of this x, because now when I go back, I can say, all right, let's start at some value of x. And so let me just be careful here. X is, again, defined as how far this is away from this point, okay? And so it's a, and then it gets smaller, and then it gets bigger. So that's going to be a little tough to write. Let me do this. let me call this axis along here. And here's where I hesitate. I want to call it X. But if I do that, I'm afraid you might confuse the X on the X-axis with the X in here, which is the X for how far is this point we're trying to get the magnetic field from the ring. You see, this X would be 0 when I'm talking about this ring that is at point A. But if I, let the origin be right here, then along the axis, that wouldn't be 0. Along the axis, that would be point A. So I'm like, what shall I do here? Why don't I do this? Right? And again, hope this isn't confusing, but I don't want to call this axis X, because I know if I do, I'm going to confuse somebody with this other X in here. And it's not traditional to call the axis horizontally Y, but I'm going to go ahead and do that. So if I do that, then watch this. This would say, and maybe I'll put it up here on the top of page 2, but this would say X is what? And so if I look closely at this, this would be a Y minus an A. That is, if I take the position I'm at and then subtract A from, that would give me how far I am away from that ring. So for example, at the beginning over here, at the origin, put it this way, when Y is equal to 0, I would get X equals to A, or actually negative A. By the way, I just noticed that would give me a negative A. I'm not going to worry about that because it's X squared. And then when I get to the other side, I would start getting to values of Y that are greater than A. And again, that value of Y minus the A would give me my distance X. For example, if I were to go all the way out to the end of my axis here, when I would say Y would be equal to L, this would then become L minus A. That's the distance away. So the last ring out here is a distance of L minus A. So this is kind of the magical piece I'm looking for in order to connect this X, which is how far is the ring from the point I'm trying to calculate the magnetic field and this axis. So maybe now you see why I wanted to make sure I didn't call this axis X, because X and Y are not equal. They're connected by this distance of A. Okay, which, by the way, probably means I need to fix what I did earlier. This then should be dy, because this would be the whole current over the whole length divided by a little current over a little bit of length. And now that little bit of length is the y-axis. So this then should be called dy, which then means back here, this should have really been a dy. But it also then means downstairs, I could put r squared plus y minus a squared to the 3/2 power. And then this would be the mu naught, the r squared, the n, the I, the L, and then there's the dy. So I'm actually adding up along a y-axis, okay? Not really an x-axis. And I probably should have realized that a little sooner so I didn't confuse you here, because I might have confused you calling this an x and that an x, and like they were the same thing, and they were not, and I didn't kind of realize it until I started substituting it in. Okay, so now finally, I think we're past the physics of it and into the math of it. I suppose we could put the limits then. This y would go from 0 on my x-axis, excuse me, my y-axis, until I get to the last ring, which is the L. And so like in any integral, I like to kind of just scan first and say, okay, what in this integral is a constant? And so the mu naught is a constant, the r squared is a constant, the number of turns is a constant, the current is a constant, the size of the solenoid L is a constant. And so it looks like in the top, I just have the integral of dy left, everything else just pulled out. And down at the bottom, the 2 can pull out. And then I get an r squared plus ay a squared, to the 3/2 power. Okay. Now, I might simplify this a little bit by maybe calling u, scratch that out, equaling to a y minus an a. So a du equals a dy. So this integral becomes mu r squared n I over 2L. And now I've got an integral of du. And then I have an r squared plus a u squared to the 3/2 power. So I wouldn't call this a u sub solution, although I did do a u sub just to make it look a little nicer. But in this format, this looks like a trig sub. This is one of those trig subs that we've done many, many times. And let me do the same thing. I remember one video I went through and did the solutions for you guys on the U sub, but I think at this point, we're probably better off to say, let's just open up the textbook and go to the Appendix B in the Survey book, or any other, your math textbook, if you like, wherever you want to look it up. But I've been mentioning Appendix B and say, well, what is this integral? And as I said, when we did Coulomb's law, we saw this. All right, so I'm going to go to the textbook here, and I guess Appendix B would be way at the end. And there's this big table of integrals. Let me make it a little bigger so I can read it. But it's the second to last one on page A-18. So A for appendix and page 18. But it says that this integral is equal to, and then they have done it in terms of x, so I'm going to just have to remember that in theirs, their x is my u, and their a is my r. So this would be then an r squared, and then this would be a square root of u squared plus r squared. I did that right. So I've got my u's and I've got my r's. Okay. I suppose even at this point, I can then notice how that would cancel off. Okay, so I've got mu naught n I over 2L here. And then now, in place of u, let me go back and put a y minus a. So then this is the square root of y minus a squared plus r squared. And now I can put kind of avoided the limits because they were back in this step here, 0 to L when we're talking about the Y, but when we switched it to a U, that would have been, well, if we put in 0, that would have negated A to an L minus A. But I never mess with that because I always then go to U and switch it back to the Y so I can just carry my limits down to whichever is easier for you. And seeing that, I can then head and let me switch back to my Zoom here. Uh-oh. Second, it froze a little bit?
Yeah, it's frozen right now. And then, oh, now it's going. Or
Yeah, let me watch it for a second, see what happens here. And see if it comes back. It's come back with a little delay. I'm gonna pull my hand away and count. 1, 1,000, 2, 1,000, 3. Well, it's only 3. Maybe it'll get better. I'm gonna keep going. See where we are. So I'll start writing mu naught Ni over 2L. Oh, finally my video is showing. And so now I can put this in as L minus A over the square root of L minus A squared plus R squared minus, and then put in my 0. So my 0 then would be A minus A over the square root of minus A squared. I'll just leave it as an A plus an R squared. And I think that might be the answer. Let me jump over to the solution page. There's a lot of steps there. Call up the solutions. And what was this, number 36? Let me scroll down. And let me just check here. And over here, I got the mu, the I, and the N over 2L. Okay, good. Oh, now they list this one first. Let me do plus here. All right, so I'll do that. I'll change those to a plus sign, and then go here. And good. Got it. Yay! Makes me feel good. And surprisingly, that was only on 2 pages. Although there's more to this question. So let me jump back to my Zoom here, see what my delay is. Debate. Okay, I think I'm going to struggle through this problem and then I'll reset. Oh, no. Oh, I think it's really bad. No, I'm going to try this. I'll move my hand in here. Ready? Move my hand. 1, 1,000. 2, 1,000. 3, 1,000. 4, 1,000. 5, 1,000. 6. Well, I'm still going to try this, even though delay. I am going to unshare, but let me just go back to the question because I think the part B will wrap it up. Part B says, show that if L becomes very, very long, that B, the magnetic field, approaches, and then they give us a little equation. All right, so maybe I'm going to put, this is the answer to A. And so I'm going to put B here and just say that as as L becomes very, very large, the B approaches the value at the end of it. Now, coming back to my original picture here, the end point would be when A is equal to 0. Let me go back to my Zoom picture so what you guys are looking at. Okay, so they are indirectly saying make L very big, but make A 0. So if I make A 0, this term goes away. The second term, cross it out. See how long the video takes before you see me cross it out. There it goes. All right. And then, of course, I would have still in the front the mu naught, the n, the I over the 2L. And then over here, the first term with A going to 0 would just be an L in the numerator. And downstairs, we essentially have an L squared because the A is 0. And what we're saying here is the R is small compared to the L. So instead of writing this as L squared plus R squared, I'll just cancel off the R squared. That's just really, really, really small. And so essentially, I just have L over L, which of course is 1. And so we just have this mu, this n, this I, and this 2, and this L. And that's what they wanted us to show. And by the way, as a side note, if we did what we all call the perfect but impossible ideal solenoid, we get this in Ampere's law for the magnetic field inside an infinitely long, imperfectly wrapped solenoid. And this is trying to say that a nice rule to remember is that even though we like to use this equation for inside the solenoid, right at the edge of the solenoid, we could say it's cut in half. It's about half of its value. And that's kind of a common engineering idea that, okay, the magnetic field inside the solenoid has this value, and at the ends, the edges of the solenoid, it's roughly cut in half. And that's what this problem is illustrating when you don't have an infinitely long, which of course no solenoid is infinitely long. So even using the equation from Ampere's law from an infinitely long one is kind of ridiculous, but nonetheless we do it. All right, well, let's see, who's that? That was Andrew. I hope that helped, Andrew. I think oh, do I see Andrew? I don't even see you.
Yeah, that helped. I'm still here.
Oh, there you are. Okay, okay. Yeah, okay. All right, well, unless anybody has a question specifically on that, let me keep moving through the questions here. And I'll go to number 27 in chapter 30. Okay, so chapter 30, number 27, and move my hand, 1,000, 2, about a second and a half delay. So I think it's caught up a little bit better. So with that in mind, maybe I'll just keep working through and see if it improves a little bit better. I can tell it's the internet because on my laptop, it shows it right away. So the Bluetooth connection between my phone and the computer is really good, but somehow from my laptop out to my desktop, it's got a delay. So I would assume it has the same delay for you guys. So I don't know if even resetting my phone would work. Oh, it has in the past. So anyways, so let me write this one down here on the side. So let's see, number 30 or chapter 30, number 27, and the time is
49 minutes, 30 seconds.
49:30. Thank you. A little more accurate there. And that other one you said was 7:20. I didn't write that one down. Nice.
7:20 was when but like you think you actually start doing the problem around 10 minutes if you want it.
Oh, would that be a better way?
I don't know. It's up to you.
Yeah. Yeah. Maybe I'll just use that word approximately again, and people then can scroll forward and back from there. Okay. All right. So I guess I gotta read the problem here. All right. So, and who asked this one? Anthony. Okay. So let me come back to my web page here, number 27. Oh, a packed bundle of 100 long, straight, insulated wires forms a cylinder. Okay, so let me draw it kind of like this. I'm going to make a big cylinder, kind of drawn off on an edge here. And then I'm going to draw tightly packed ones, maybe starting in the center here and moving out. And maybe that's enough to draw. But the key to remember is that, and I'll just put N is 100, and the current in each of them is 2 amps. Let me just read it again. A packed bundle of 100 long, straight, insulated wires forms a cylinder of radius. Oh, I didn't read the radius. So R equals a half of a centimeter. If each wire carries 2 amps, what is the magnitude and the direction of the magnetic force per unit length acting on a wire that is 0.2 centimeters from the center of the bundle? And so maybe in a different color, I'll draw a distance of 0.2 centimeters. And they want me to find the force on this per unit length. Okay. And so this, I guess, begins really with chapter 29. We learned in 29 that the force on a wire carrying a current would be I and L cross B. Maybe a little bit better would be say it was an integral of I ds cross B. But for this special case, where your wire is straight and there's no changing of the magnetic field, I being the same, B being the same, the angle being the same, this integral of ds just becomes the length. And that's what's going to happen here. Maybe I need to convince you of that. Let's begin with saying, okay, what is the current and the direction of the current? So the current they're talking about would be the current on this long wire that is 0.2 centimeters from the center. I'm trying to find the force on that wire. So clearly that current is a constant. It's the 2 amps, and clearly it is in the same direction. It's a long, straight wire. But it begs the question of what is the magnetic field, and that's where Ampere's law comes into play, and that's where this chapter comes into play. I did it in the lecture, not quite like a problem like this, but we did it in the lecture by saying, what if you had a wire where the current was uniformly distributed all the way through it? And so if you made an Amperean loop, and I'm trying to remember, maybe I need to go back to the textbook, what color your author use for Ampean loops? Now that I got my colored markers, he was drawing Ampean loops in blue. Okay, so grabbing my blue here, if I were to make an Ampean loop and apply Ampere's law, it has the similarities of Gauss's law. By the way, this was my warning to you last Sunday when I sent this out. We're basically going to do Coulomb's law and Gauss's law, but we're going to do it with magnetism. And so I guess I already showed in the last problem what would be the equivalent of Coulomb's law by adding up a bunch of rings. Now I'm trying to show you what's the equivalent of Gauss's law by looking at the current that is, and I should have put here inside, the Ampean loop. Now, of course, what's different is Gauss's law did a volume, and so it was the charge enclosed in a volume. This is the current that goes through an area, so it's like one-dimensional lower. So we do integral along the edge of the loop. In calculus, we would call this a line integral, whereas in Gauss's law, we did a flux integral, we did a surface integral. So everything's one-dimensional lower. Gauss's law, if I put Gauss's law right here, Gauss's law said the integral of E dot dA. See, it was the electric field through a surface, where this is the magnetic field along a line. And then it would be equal to the charge inside. So it would be the charge inside a three-dimensional volume. Whereas here, this is the current inside or going through the loop. So it's through a surface, 2 dimensions. But other than that, it's exactly kind of that same thing. So let's go through the same arguments that we did for Gauss's law. And the first one is to take the dot product and do our symmetry arguments. And so let me repeat our symmetry arguments like we did with Gauss's law. If you think of this, and here's the real problem, that has 100 of these wires uniformly distributed, so I'm going to think of it as just a total of 200 amps uniformly distributed. If you make an Ampean loop and you were to stand somewhere on this Ampean loop, as you look around the current, it would look the same to you standing here as here as here. And so that means the argument is that the B, whatever it is, that's what we're trying to find, would be the same everywhere on the Ampean loop. And so that dot product for Gauss's law, and now the dot product for Ampere's law, is the magical trick is to pick the right, in this case, a loop, or in Gauss's law, a surface, that you could argue that it would be the same everywhere on that loop surface, and you can pull it in front of the integral. And so that's why this circular Ampean loop is so powerful, because I could argue that no matter where I stand on this Ampean loop, the field would be the same. If I had made a square or an oval or basically any other shape but a circle, I could not argue that the field would be the same everywhere on that oval, and I couldn't pull it out in front, and I'd kind of be dead in the water. Unless you know some fancier calculus like Green's theorem and Stokes' theorem, I'm kind of dead in the water. So for our level, I would just say we're dead in the water, but I'll throw that out there for next semester or next year when you guys transfer and you take your magnetism classes again. You will have the power of things like Stokes' theorem and Green's theorem, that you can do some fancy manipulation with stuff inside of the integral. But for us, this is the approach we're going to take as a beginning student here, that we just got to get the right loop for this to work. Now, the other part of it is the angle between them. And so again, just like in Gauss's law, picking that right angle is crucial. And so again, we could argue that the magnetic field has to be along this direction of the Ampean loop. There's a couple ways of arguing that. Probably the best one is a line of symmetry. Maybe I'll use a different color and draw. Well, that's kind of too close to red. Maybe I'll draw a line of symmetry. But if you flipped this whole thing, you would get current going in the opposite direction. So we did a lot of symmetry arguments when we did Gauss's law. We're going to do a lot of anti-symmetry arguments for Ampere's law. That is, if you were to flip it around this line of symmetry, the current wouldn't be the same. The current would be same magnitude, but opposite in direction. So the magnetic field must flip. And to do that, that means the direction of the field must be perpendicular to a line of symmetry. Because when you flip it, now the magnetic field would flip around and be exactly in the opposite direction. And so we're going to take advantage of the anti-symmetry of it, not the symmetry of it. So that's our argument, that we know the direction of the magnetic field. Even though we may have never even seen this problem or never have done it before, just the fact that symmetry, or in this case, anti-symmetry, would tell me it's perpendicular to a line of symmetry. That would tell me the magnetic field is in the direction of the loop. And then this angle here is the angle between B and the direction of the loop. So this would tell me that has to be 0 degrees, which would tell me this just becomes a ds, which then that's just their circumference. And so that is B times 2 pi. And so that's the, I guess, the left-hand side of this Ampere's law. Now, the other side of this is this mu naught, and then it would be the current that is inside of my Ampean loop. So let me write it then as the sum bunch of current and come back to my picture. I'm going to be adding up all the current that is inside of my Ampean loop. It's not full current. And in this case, the full current would be representing 200 amps, because it would be 2 amps in each wire times 100 wires. And that's not what I have. So this number is something less than the 200 amps. And of course, we did the same thing with Gauss's law. We said, what would be the electric field when you're inside a ball of charge? When we're outside the ball of charge, we just said the charge was all the charge on the ball. And I would do the same thing if I was trying to calculate the magnetic field outside of the wire. If I was trying to find the magnetic field outside of the wire, I would say the current is all the current, the whole 200 amps. But in this case, I don't have all the current. So I have to do a little integral and realize it's going to come out to be a fraction. Then this is where the current density comes into a useful play. And so we just remind you that current density is the amount of current in a given area. And they were nice to me because they made the current density uniform. That is, they said everyone in here has the same 2 amps. So the right-hand side of the equation then just becomes this area, where the area is the area enclosed by my Ampean loop. I didn't put a symbol here, but if I put a lowercase r for the radius, then this would be pi little r squared. which is what I was kind of implying back when I did the circumference of the ambient loop. I put a little r. So I didn't put it in my picture. Let me do that now, but that would be the area. Of course, another nice step here is for current density, I could take all current. So let me call this I, all the current. That's the full 200 amps over pi times the whole radius. And so, I guess we're running out of room on that piece of paper. I would have the equation. And let's see what I have so far. So I got B times 2 pi r equals mu naught I. And I'll just repeat, since I'm on a new page, the same equation. But I'll cross out the pi's, top and bottom. And I'll even cross out a little r, left and right. And I get a mu naught, an I, an r in the top. And in the bottom, I get 2 pi over a capital R. And let me put a box around it. Well, part of me was thinking maybe to save a little time, I should just start with that equation because it was derived for you both in the lecture and in the textbook. But I decided, no, why don't I go ahead and run through Ampere's law. And so now that I ran through Ampere's law, let me come back to page 1. And remember why we were doing this. We were trying to show that the magnetic field then has the same value and is at the same angle for everywhere across here, so we could justify changing this integral into this form. And so I guess I would say I've just done that. And so to answer the question, I would have the current in that wire times the length of that wire across the magnetic field. So as I put my numbers in here, this is my current, 2 amps. The length of it, let me just call that L, because all I said is it was a long wire. The strength of the magnetic field, we just did, it's mu naught times the total current. Let me put that as 200 amps times the R over the 2 pi, and then the R squared, which they said was a half a centimeter. So let me put that as 0.0005 meters. Maybe I could even put the R, they wanted me to find it at 0.0002 meters. And I guess for completeness then, I would have sine of 90 degrees. So I'll put that, but remember this is the cross product, and so we're looking at the angle between the magnetic field and the wire, which back on page 1, we argued that it would have to be, the magnetic field would have to be along the direction of the ambient loop, and that is perpendicular to the long wire that's angled back. So that's where the 90 degrees came from. And so finally, I could put the L to the other side of the equation, and I would have the 2 amps times the 4 pi times 10 to the -7 here, the 200 amps for the total current, position I'm trying to find the field, 0.0002, over, there's a 2 pi, 0.0005 squared. And so that would be the force per unit length. And so maybe just crossing out a little bit before I actually put these numbers into my calculator. I've got a 2 times a 2 to the negative 7th times a 200 times a 0.123 divided by 0.123 squared gives me a 0.064, and this would be newtons per meter. And of course, not complete until you get direction. And so here is the equation for the force with the cross product. And so I'm going to get my right hand ready here. My right hand needs to have my fingers turn here so I can do a cross product. And so the first thing is, what's the first vector, which is L, the direction of the current. So coming back to page 1, and kind of in my model, I had the current going back into my paper, kind of on my paper from a right to a left. Okay. And so my current is going in this direction. Now, I also need to know the direction of the magnetic field, and so maybe I'll put the Ampere loop here. Using something from the B-ups of art, if I put my thumb in the direction the current is going, my fingers on my right hand will curl around. Maybe I'll hold my right hand upward so you can see my fingers curling. This then would be the direction of the magnetic field. So in my drawing, the magnetic field would be a circle. It would be along the Ampere loop. That's what we argued here because of the anti-symmetry. But it would be in a, let's see, this would be a clockwise direction. So down here, this wire is, the magnetic field would be pointing something like this in the picture. So if I take my right hand to do the cross product, I would put my fingers in the direction of the current, close towards the magnetic field, and that would give me a force that is, for this wire, upward or towards the center. And if I do that on any other wire along this Ampere loop, it would always give me a force pointing inward. So coming back to finishing up the problem, I already got the number. Now I guess I need to say it is inward. And so this bundle of wires magnetically are attracted to each other. I think that's one thing you got out of section 2, at least I hope, that two wires that travel in the same direction, if the currents are in the same direction, they get pulled together. And wires that are in opposite direction get pushed apart. So these are all in the same direction, and so they're actually magnetically being pulled together. Now, not much, but it is, some value that they are being held together. If you tried to, took off the insulation and pulled on them, they'd be kind of sticky. They would want to hold each other and grab each other.
Dr. Young, I have a question. Would you be able to show us one more time how you got the direction of B, please?
I will. And before that, I'm just going to flip back over and check the solution on 27. See if I got anything close. They got, oh, now they got times 10 to the negative 3. Oh, my bad. Okay. I haven't forgotten you, Gina. I'm coming to your question. I treated these as millimeters for some reason. And so I apologize. Let me come back to the question. They said a half a centimeter and then 0.2 centimeters. And centimeter is only 2 decimal places. So let me fix that. So this should be 0.002. And this should be 0.005. And I believe that would give me one more decimal place, but I'm going to try that again. So 2 times, and then this would be 2 times 10 to the negative 7 times, there's the current, 200, and the 0.002, then divided by 0.005 squared, and then I get a 0.0064. Okay, so sorry about that. All right. Okay, so now we match, and let me see, did they say inward also? Yeah, they say inward also. And by the way, I haven't forgotten about you, Gina, but part B then just says, where would the force be the greatest? And so just coming back to this equation, you can see that it ends up being the greatest when this R is as big as it can get. And so the R, the biggest it can get would be up on the surface, the whole half a centimeter of the bundle. So the magnetic field keeps getting stronger until you get to the edge here. And so the wires that make the perimeter are the ones that are getting the most inward magnetic push, pull, whatever you want to call that, inward. They attract the most. And that really comes back to really this statement here, that the magnetic field gets stronger as you get further away, at least to the edge of the wire. Now, once you get outside of the wire, this equation wouldn't be valid anymore. And so I don't want to use this equation for outside of the wire. But the biggest little r can be and still be inside of the wire is equal to capital R. So at that point, the field would be this strength on the surface. So that's where the force would be the most. So anyway, so that's B. So maybe I should put this as the answer to A, and the answer to B would be on the wire's surface, or the bundle's surface. So we've got them bundled together. Okay, now, Gina, great question. It's hard to see and kind of hard to demonstrate here in a video. It takes kind of this three-dimensional view here. But you just asked the direction of the magnetic field, not the cross product, although I'll do the cross product again also. Let me try to draw a new picture here. In fact, let me go back to my Zoom so I can see if I'm behind at all. So let me draw kind of a big circle. Okay, good. There's only about a second delay. And let me think of this as this wire going back. Okay. And in blue, let me draw an Amperean loop. Okay. Now, let me remind you that the current is all headed back here. And maybe for simplicity, let's just think of this wire as the, one solid wire, not really made up of 200 different pieces. So it's all flowing in that direction. And imagine us, and I know this wasn't quite your question, Gina, but I'm gonna do it anyways. When we go to look at Ampere's law, since we have to do this integral of B dot ds, we would want to ask ourselves something about being on this Gaussian surface. Do we know anything about it? I'll draw 6 points along this Gaussian, oh, sorry, I said Gaussian, Amperean loop, sorry. We have to say along this Amperean loop, what do I know? Well, I know the magnetic field comes from the current. And so I'm standing at point number 1 versus point number 2 versus point number 3. I would essentially see the same pattern of current that is passing me. So that argument tells me that whatever the magnetic field is at 1, it's the same at 2, it's the same at 3, it's the same at 4, it's the same at 5, it's the same at 6, and it's the same everywhere. So that's how I then argue my point that the magnetic field is a constant. And so I know that wasn't your question, Gina, but I thought I would just emphasize that I'm looking at the physics of what makes the magnetic field. What makes the magnetic field is the flowing of this current. All right. Now I can finally get to your point, and that is I'm going to then just draw a line right across the center of my Amperean loop. And so I will draw it from 1 to 4. And this is the key. What makes the magnetic field again? Well, what makes the magnetic field is the flowing of the currents. Okay, so what if I were to take this whole thing and flip it? It makes me wish I had drawn it on this Post-it. So here it is on the Post-it, and what happens if I flip it? Well, if I flip it, the currents, and let me say it again, the current is what makes the field. And so if I flip it, the current now is flowing the other direction. But besides going the other direction, it still looks the same. It's still the 200 amps. It still is evenly distributed. And so I would use that argument, and we call this an anti-symmetry arc, because when you flip it, something does change, the direction of the current. Everything else stays the same. So I would use the argument that when I flip it, I now have a field that must be opposite of what it was before. Because again, I'll say it, the current is what makes the field. And the current is now flowing in the opposite direction. It would be the same strength because the magnitude of the current still looks the same. The distribution of the current still looks the same. But the direction is reversed. That's the only thing that's reversed, and hence the name anti-symmetry. So wherever the direction of the field is, it must be in such a direction that when I flip it, it is now going to point in the other direction. So maybe I'll make some guesses. If this is this line of my flip, if the magnetic field was pointing maybe in the same direction as this green line. If I flip it, it's still pointing in the same direction. It did not go in the opposite direction. So it doesn't fit the criteria of an anti-symmetry. It's not being flipped. It's actually going in the same direction. In fact, these are the arguments we did for the electric field. In the electric field, we said we had a lot of symmetry. And because of the symmetry, when we flipped it, if we had the same charge distribution, the electric field must be still in the same direction. So that's how we argue that the field must be along a direction of symmetry. Now I'm going to argue that it can't be along a direction of symmetry, because when you flip it, you must get a field that's opposite, because the current is going in the opposite direction. So where would that be? Would it be down at an angle like this? Well, no, because when I flip it, it goes off to an angle to the left. So it started off to an angle to the right. When I flip it, now it's off to the left. But that's not opposite. They're still down. This is just down to the right, and this is down to the left. So what direction would actually flip? And the only thing that would actually flip would be a direction that is perpendicular to a line of symmetry. So when you have an anti-symmetry for the current, you know that the direction of the field it makes, so the magnetic field, would be perpendicular to a line of symmetry. And so again, for Gauss's law, we did a lot of symmetry arguments. Now I'm going to do a lot of anti-symmetry arguments. So that magnetic field must be perpendicular to a line of symmetry. So if you come back to the original, there's a line of symmetry, there's a line of symmetry. I've got a lot of line of symmetries, and the magnetic field must be perpendicular to that. So the magnetic field must be along the direction of the Amperean loop. And of course, there's one more step, because at this point, I don't know if it is in a clockwise direction or a counterclockwise direction. But here's where I'm going to take advantage of what we had done with Biep's of art. And of course, this is just a human definition. We could have defined it. The physics tells us it has to be perpendicular, but the direction we as humans want to draw our arrowhead is just a human choice. That's why from the physics, I can't argue whether this is clockwise or counterclockwise. I can just argue that this is the way we decided to draw our arrowheads. We decided to draw our arrowheads the direction a compass would point, which means the arrowheads go from a south pole to a north pole. Well, geographic. I shouldn't have said it that way. So they point from a magnetic north pole to a magnetic south pole. That's the way I should have said it. But with that definition, then, we learned earlier in this chapter that if you just had a long wire, I'll get a clean piece of paper here. That definition is kind of easily seen by saying if you have a wire and with the current flowing in the wire, our definition allows us to use our right hand. Could have been defined just as easily with our left hand. But it turns out to be that if you take your right hand and you hold it in kind of a thumbs up position, and you treat your thumb, that's a straight line, as the current, then your fingers, which are making loops, would represent the magnetic field. And so our magnetic field would be like grabbing the wire with your right hand and making a loop. So if we go back to our problem, I would use my right hand and put my thumb in the direction and look at my fingers. And maybe I'll stand up to kind of hold it down, but you can see my fingers then are going in kind of a clockwise direction. So that means the field would be pointing this way, the opposite way that I drew them originally here, now that I give it some thought. And so the field would be along the Ampean loop, so it'd be a circle along the Ampean loop. And looking at it over here to my right, looking down the wire, they would be pointing in a clockwise direction. So that's how I got the direction whole argument. It's an anti-symmetry argument plus the definition. And a good way to remember the definition is to use our right hand.
Okay, thank you. If you have time, are you able to explain why using Ampere's law, how you figured that the left-hand side was not the capital R?
The
I got my R's confused.
left-hand side. Okay, yeah. So coming back to page 1, the meaning behind here is to add up the magnetic field on the Ampean loop. So it sounds like you got the argument here that I took the dot product and argued that the magnetic field would be a constant on the Ampean loop, so we pulled it in front of the integral. And now we argued that the magnetic field would be, at least from anti-symmetry, would either have to be 0 degrees or 180 degrees. From anti-symmetry, we can't really say which one it is. We have to have a human definition for that. But either way, that just is either a +1 or a -1. So this gives us the magnitude. But once we know that, then we just have an integral of this ds. And I think this is the heart of your question, is then this integral says add up the Ampean loop. So I didn't actually do this integral. I more read the math than did the math, because this is saying add up the little pieces until you go all the way around the Ampean loop. And that's going to be the circumference. And so the circumference is 2 pi r. And your question then is, well, which r do I use? And I would say, coming back here to the meaning of this is saying what is the adding up of the Ampean loop. So this would be the length of the Ampean loop. And so that's the little r, because big R is the circumference of the wire. And that's not what this says. This is not saying add up the magnetic field along the outside circumference of the wire. This is saying add up the magnetic field on this mathematical loop, this Ampean loop. And so that's how I got the radius to be a little r, not a big R, by knowing what was I adding up. I was adding up the loop, the Ampean loop that I drew and I created in order to help me solve the problem.
Okay, so the bundle extends outside the Ampean loop?
Yes, because I am trying to find, back to this problem, I'm trying to find the force on a wire that is just partway out. I kind of scribbled over it now, but they say 0.2 centimeters out. And so in order to do that, I began with my information from chapter 29, which was to say, I know the force on a current in a magnetic field. And so I just need to figure out a way to get the magnetic field where this wire is. And this wire is actually inside of the bundle somewhere. It is not on the perimeter. Oh, I shouldn't say perimeter. Your math teacher will freak out. On the circumference of the wire. And it's certainly not outside of the bundle. but it is inside. So yes, I am making an Amplian loop that is inside, and that's why my Amplian loop has a radius that is smaller than the radius of the whole bundle. I want to find that magnetic field where that wire is, so I can find the force on that wire.
All right. Thank you.
Yeah, 2 long, hard, good ones. Yeah, really good. Jonah. Hey, talk to me, Jonah.
Hello.
Hello. Should I try to do yours even though we're after time, or should I take a break? Are you going to be back here at 12:30?
I can come back. That's no problem.
Okay. If it's not a problem, why don't I write down these questions so I don't lose them? And so I will go here, Jonah. Let's see if I log off. Oh, I know what I'll do. Yeah, I'll just take a quick picture of it, and then, but I'll make sure I turn off my phone first. All right. So Jonah, you're first when we come back, and then we will go to, looks like Daniel with question number 3, and then we'll go to number 17. And then we got another 121 coming. All right.
Great.
That work for you guys?
And that's at 12:30?
Yeah.
Okay, cool. See you then.
All right. See you guys.
Yeah.